Nuclear and particle physics have been a very important part of the entire subject of physics, and its practitioners have won an impressive number of Nobel Prizes, maybe the largest number compared to any other topic in physics. The study of subatomic particles and their properties has given scientists a better understanding of the nature of matter and energy, and of course, the origin of universe. Despite more than a century of research, the subject nuclear and particle physics remain exciting and vibrant with many interesting phenomena still being discovered and problems awaiting solutions. It was a common practice to teach the two subjects together, and the scheme was followed by many Indian universities till recently, when the topics become so vast that no single course can do justice to both subjects. Thus, treating them separately become inevitable, and it is advisable to include the two topics as separate courses in subsequent semesters. To understand the basic concepts of particle physics, fairly good knowledge of quantum mechanics and nuclear physics is required. However, in this lecture series, the required knowledge of quantum mechanics and nuclear physics is kept at a very basic level that the students in graduate class can follow them easily. Students are advised to read textbooks for more information and clarity, because no lecture class can be the replacement of a standard textbook, and the lecture notes are not going to fill up the gap of understanding any subject from its basics to advanced level. In the first lecture, we study the classification and properties of elementary particles, which are the building block of universe. There are many good textbooks available for various levels, and students can select them according to their requirements. A few graduate level texts is listed below. The first one by Griffith is an extremely nice, and the author, through his lucid way of presentation, make the subject very interesting. The concept that the world is made up of fundamental particles has a long history. The idea put forward by Dalton that atoms are the indivisible building block of matter can be considered as the first convincing suggestion in the history of particle physics. However, the observation of characteristic spectra of elements suggested that the atoms have their own internal structure. The discovery of electrons by J.J. Thomson, followed by Rutherford's scattering experiment using alpha particles, proved that the atoms consist of negatively and positively charged particles. Then the scientists came to a comfortable situation with the assumption that the complete universe is made up of some 90 plus elements, with the support of chemistry that was developed to a remarkable level by that time. It was logical to believe that the atoms of different elements consist of different number of electrons revolving around the nucleus, which has a heavier mass and comprising an equal number of positive charges. Later, it was discovered that nuclei consist of neutrons and protons. At this stage, again, a satisfactory situation was evolved. All matter appeared to be composed of various combinations of three elementary particles, the neutron and proton, held together by strong nuclear force, and electrons revolving around it, satisfying Coulomb's law of forces and quantum conditions. However, the confidence was short-lived with the discovery of more number of elementary particles, neutrinos, mesons, and quarks. The probing continued, leading to the discovery of muons and pi mesons, followed by many other related mesons, and even larger number of particles associated with the neutrons and protons. At present, the number of particles is too large and difficult to classify in a unique way, but is still possible to assume that the universe may possibly be composed of various combinations of some set of elementary particles known and unknown till today. More than 200 subatomic particles have been detected so far. Most of them are highly unstable, existing for 1 millionth of a second or less, and are produced as a result of the collisions in the cosmic ray reactions or particle accelerator experiments. electrons and quarks containing no discernible structure, that is, they cannot be reduced or separated into smaller components. So, it is reasonable to call them as elementary particles, though the name in the past was mistakenly given to the particles such as proton and neutrons, which we know now has complex structure containing quarks. The term subatomic particles refers to both true elementary particles such as quarks and electrons and also to the larger particles that form quarks. There exist matter particles and force or field particles. Quarks and electrons are matter particles, whereas photons and gluons are force particles. In the standard model, all of the matter particles are fermions, whereas field particles are bosons. These two classes of particles have different symmetry properties that affect their behavior, details of which will be discussed later. It is important to mention here four kinds of natural forces. Gravity and electromagnetism are well known at the macroscopic level. The other two forces act only on subatomic scale, indeed on subnuclear scale. The strong force binds quarks together within protons and neutrons, whereas electromagnetic force, which is responsible for holding bulk matter together, the strong force keeps protons and neutrons within atomic nuclei. Unlike the strong force, which act only between quarks, the weak force act on both quarks and leptons. This force is responsible for beta decay and also for nuclear reactions that fuel sun and other stars. Every particle, massive or massless, is subject to gravitational interaction. Particles that are electrically charged experience electromagnetic interaction. There is no classical analog for the strong interaction responsible for binding nucleons inside a nucleus, and also weak interactions which figures itself in decay process. These two are short-ranged forces, unlike the electromagnetic and gravity, which are long-ranged. All the fundamental interactions are possible via the exchange of some elementary particles, which are bosons. These particles are known by various names such as messenger particles, force carriers, intermediate bosons, or gauge bosons. Many a time, when these particles are involved in interactions, they cannot be observed because they act as virtual particles. There are various ways for the classification of elementary particles. We know that there are charged and neutral particles. Electron is the first particle discovered and is negatively charged, followed by protons, the positively charged particles, and neutrons with no charge. Based on spin, particles can be classified as fermions and bosons. Fermions with half integral spin and bosons with integral spin. Particles can also be classified based on the interactions like strong, weak, electromagnetic, and gravitational. These forces of interaction are mediated by intermediate particles or exchange particles. Photons are the exchange particles for electromagnetic interactions, gluons for strong, W and Z bosons for weak, and finally gravitons for gravitational interaction. Another fruitful method for the classification of elementary particles is based on their mass. Leptons for light particles and hadrons for heavy. Hadrons are further classified into mesons and baryons. Baryons are the heaviest particles known, followed by mesons. Pions and kaons are examples of mesons, whereas protons and neutrons are examples of baryons. Electrons and neutrinos are examples of leptons. One of the major limitations of the above method of classification is that an important class of particles, photons, is not included in the above group. This is anyway expected because our classification is based on mass and photons are energy particles with restive mass equal to 0. At the same time, massless particles such as neutrinos crept into the group through leptons. This means that whatever be the method of classification, some particles are always left or some may find in different groups. For example, classification based on spin, some bosons and fermions share certain common properties. Classification shown in the next slide is more elaborate and give better insight into the field of elementary particles. Photon is the first particle identified with almost complete properties known first as electromagnetic waves from the study of spectral lines and then as particles. Actually, the entire electromagnetic spectrum from gamma rays to radio waves was well known much before their identification as particles. Leptons are classified into electrons, muons, tauons, and neutrinos. Electrons are negatively charged particles with spin half and infinite lifetime. Muons are elementary particles similar to electron with an electric charge -1 e and a spin half, but with a much greater mass, approximately 207 times that of electron. Lifetime of muon is 2.2 microseconds, which is very high compared to other unstable particles. Tauons are negatively charged particles -1 e with spin half similar to that of electrons. Mean lifetime is about 2.9 multiplied by 10 to the power -13 seconds and 3477 times heavier. Tau is the only lepton massive enough to decay into hadrons, particularly into pions. And finally, neutrino is a lepton with a spin half but has no electrical charge and a very small mass which might even be equal to 0. Neutrinos are one of the most abundant particles in the universe, and because they have very little interaction with matter, it is incredibly difficult to detect them. Discovery of neutrino has far-reaching consequences in nuclear physics, including the theoretical explanation of beta emission, conservation of angular momentum, etc. There are three kinds of neutrino: electron neutrino, muon neutrino, and tau neutrinos. Hadron is any member of a class of subatomic particles that are built from quarks and react through the agency of strong force. All observed subatomic particles except the gauge bosons and leptons are hadrons, except for protons and neutrons that are bound in the atomic nuclei. All hadrons have short lives and are produced in the high energy collision of subatomic particles. The other three basic forces of nature also affect hadron behavior. That is, all hadrons are subjected to gravitation. Charged hadrons obey laws of electromagnetism. Some hadrons break up by the way of weak force, as in radioactive decay, while others decay via the strong and electromagnetic force. The hadrons are classified into mesons and baryons. Mesons are further classified into pi meson, eta meson, and k meson. In particle physics, resonance, an extremely short-lived phenomenon associated with hadrons that decay via strong nuclear force. This force is so powerful that it allows resonance to exist only for that amount of time it takes light to cross each such object, say nucleon distance. Resonance occurs when the net energy of the colliding subatomic particle is just enough to produce its rest mass, and the strong force then causes to disintegrate within approximately 10 to the power minus 23 seconds. Properties of subatomic particles and the important interactions will be discussed in detail in the subsequent lectures. The entire list of elementary particles is grouped in three generations of matter and their force carriers. To explain three generations of matter, we need to understand the standard model in particle physics. The standard model explains how the basic building blocks of matter interact and are governed by four fundamental forces. Standard model is the combination of two theories of particle physics into a single framework to describe all interactions of subatomic particles, except those due to gravity. The two components of the standard model are electroweak theory and quantum chromodynamics. The electroweak theory describes interactions via electromagnetic and weak forces, whereas quantum chromodynamics is the theory of strong nuclear force. Both these theories are gauge field theories which describe the interactions between particles in terms of exchange of intermediate or messenger particles that have one unit of intrinsic angular momentum, that is spin s equal to 1. In addition to those force-carrying particles, the standard model encompasses two families of spin-half subatomic particles that build up matter. These particles are the quarks and the leptons, and there are six varieties or flavors of each related in pairs in three generations of increasing mass. The six quarks paired in three generations, the up quark and the down quark form the first generation, followed by the charm and strange, then the top and bottom. Quarks also come in three different colors and only mix in such a way as to form colorless objects. The six leptons are similarly arranged in three generations: the electron and the electron neutrino, muon and the muon neutrino, and the tauon and the tauon neutrino. The electron, muon, and the tauon all have an electric charge and a sizable mass, whereas the neutrinos are electrically neutral and have very little mass. Everyday matter is built from the members of the lightest generation, the up and down quarks that make up the protons and neutrons of atomic nuclei. The electrons that orbit within atoms and participate in binding atoms together to make molecules and more complex structures. The electron neutrino plays a role in radioactivity and so influences the stability of matter. Heavier types of quarks and leptons have been discovered in studies of high energy particle interactions both at scientific laboratories with particle accelerators and in the natural reactions of high energy cosmic ray particles in the atmosphere. Mass, charge, and spin associated with each particle is shown in the corresponding cell. We can see that the first column shows the first generation of matter and has the lowest mass. The second column shows the second generation with the intermediate mass, and the third column the third generation with the highest mass. The corresponding antiparticles are shown in the next three columns. Field particles or force carriers, that is gluons, photons, W and Z bosons, are shown in the seventh column. In the last column, we have Higgs bosons. The pictorial representation of quarks, leptons, and gauge bosons are shown here. Proton is made up of two up quarks and one down quark, whereas neutron contains two down quarks and one up quark to make its charge equal to 0. Higgs boson is a fundamental particle associated with the Higgs field, a field that gives mass to the fundamental particles. Higgs field is different from other fields such as electromagnetic field. First, it has no spin, that is S is equal to 0. For other vector fields, field particles, S is equal to 1. Higgs field is a scalar field. Further, it has an unusual property, that is, its energy is higher when the field is 0 than when it is non-zero. Details will be discussed later. The Standard Model has proved a highly successful framework for predicting the interactions of quarks and leptons with great accuracy. Yet, it has a number of weaknesses that led physicists to search for a more complete theory of subatomic particles and their interactions. The present Standard Model, for example, cannot explain why there are three generations of quarks and leptons. It makes no prediction of the masses of the quarks and the leptons, nor of the strength of the various interactions. Physicists hope that by probing the Standard Model in detail and making highly accurate measurements, they will discover a more complete theory known as Grand Unified Theory, which uses a single theoretical structure to describe the strong, weak, and the electromagnetic fields. However, Grand Unified Theory will still not include gravity. The problem here is that the theorists do not yet know how to formulate a workable quantum field theory of gravity based on the exchange of graviton. The field particle is still to be discovered. Finally, we have all the ingredients of matter grouped into 6 quarks, 6 leptons, and a few field particles to create the entire universe. The matter energy content of the universe is shown in this picture. Matter is 30.6% of the universe matter energy composition, in which 30.1% in the form of dark matter. Only 0.5% is in the mass of stars, and 0.03% is in the form of elements heavier than hydrogen. The rest is dark matter, that is, a component of the universe whose presence is discerned from its gravitational attraction rather than its luminosity. Two varieties of dark matter have been found to exist. The first variety is about 4.5% of the universe and is made of the familiar baryons such as protons and neutrons, which also make up the luminous stars and galaxies. Most of this baryonic dark matter is expected to exist in the form of gas in and between the galaxies. This baryonic or ordinary component of dark matter has been determined by measuring the abundance of elements heavier than hydrogen that were created in the first few minutes after the Big Bang occurred 13.8 billion years ago. Dark matter makes up 30.1% of the matter energy composition of the universe. Now it is indispensable to introduce Feynman diagrams to proceed with the study of elementary particles. Feynman diagram, a graphical method of representing the interactions of elementary particles invented by American physicist Richard Feynman and introduced during the development of the theory of quantum electrodynamics as an aid for visualizing and calculating the effect of electromagnetic interactions among the electrons and photons. Feynman diagrams are now used to depict all types of particle interactions. It is a two-dimensional representation in which one axis, usually the horizontal axis, is chosen to represent space, while the second one, vertical axis, represents time. Straight lines are used to depict fermions such as electrons, and wavy lines are used for bosons such as photons. On a conceptual level, fermions may be regarded as matter particles which experience the effect of a force arising from the exchange of bosons, the so-called force carrier or field particles. At the quantum level, the interactions of fermions occur through the emission and absorption of the field particles associated with the fundamental interactions of matter, in particular the electromagnetic force, the strong force, and the weak force. The basic interaction therefore appears on a Feynman diagram as a vertex, that is, a junction of three lines. In this way, the path of the electron appears as two straight lines connected to a third wavy line where the electrons emit or absorb a photon. Anyway, the selection of space-time axis is not unique. Certain authors use horizontal axis to represent time. Feynman diagrams are used by physicists to make very precise calculations of the probability of any given process, such as electron-electron scattering in quantum electrodynamics. The calculations must include terms equivalent to all the lines representing propagating particles and all the vertices representing interactions as shown in the diagram. In addition, since a given process can be represented by many possible Feynman diagrams, the contributions of every possible diagram must be entered into the calculations of total probability that a particular process will occur. Comparison to the results of these calculations with experimental measurements have revealed an extraordinary level of accuracy, sometimes with agreement to 9 significant digits. The first figure shows the Feynman diagrams of the interactions of an electron with electromagnetic field. The basic vertex V shows the emission of a photon by an electron. The second figure shows one of the simplest interactions between two electrons. The two vertices V1 and V2 represent the emission and absorption of a photon. Feynman diagram of the annihilation of an electron-positron pair is shown in the third diagram. The annihilation of the particle-antiparticle pairs lead to the formation of a muon and an anti-muon. Both antiparticles E plus and mu plus are represented as particles moving backward in time. That is, the arrowheads are reversed as shown in the diagram. Feynman diagram of a complex interaction between two electrons involving four vertices V1, V2, V3, V4 and an electron-positron loop is shown in the fourth diagram. This is a typical Feynman diagram for the elastic and inelastic electron-proton scattering. The space coordinate is the ordinate and time is the abscissa. The electron E and proton P approach each other and exchange a virtual photon, after which the electron goes off in one direction and either a proton or some group of particles of net mass W go off in the other direction. In the inelastic case, the electron's energy changes in the interaction from E to E dash, with the virtual photon carrying off the energy difference E minus E dash. Large amount of materials are available in the internet, published by famous laboratories, university websites, and reputed authors. For example, Physics for 21st Century Building Blocks of Matter. Students are requested to utilize these materials for their studies and for a better understanding of the subject. Forthcoming lectures will explain properties of elementary particles and their interactions with the support of necessary theory and experimental data.